Hello everybody, this is Scott Darmus. Recently I've been working on a new prediction of my theory, which this time is in quantum mechanics, which is quite unusual because my quantum gravity theory normally makes predictions about gravity, cosmology, and sometimes particle physics. But so far I've always claimed that my theory leaves quantum mechanics pretty much untouched. Well, that's not really the case. Already in the very early days of my theory in 2005, I've said that as the wave function goes up and down, um, the particle, which is a complex sphere, disappears and reappears continuously. And that actually means that, unlike in quantum mechanics, the probability to detect a particle on one straight line, let's say a direct line from the emitter, um, it's not constant like it is in quantum mechanics where you just take the absolute value and you always get the same probability. But here the probability goes up and down like a wave. And from that you would expect that if you have a laser that is laser like this one here on the floor, laser that is possibly phase coherent, like you get the same. And I think that's I mean, laser light is coherent light, so there should be quite a bit of phase coherence there. If you have phase coherence, then let's say you have laser light, it lands on a screen, detector screen, if you will. You would expect there to be a lot of bright and dark spots with kind of fixed positions. Well, it depends on how much phase coherence you have. So let's say this is the straight line, and this is your wave. The detector screen is here, and the wave goes up and down like that. And on the screen it's zero. And then you can look, if you change the angle and you go up here, how far up do you have to go to again be at zero here? You can calculate it using this formula here, and you find that it's the angle that you have to change, the minimal angle, is 0.026 degrees. And that's based on a wavelength of 650 nanometers at a distance of about 3 meters. So then what you get is the first distance is 1.4 millimeters, and then 0.5. So you get basically concentric rings, where concentric dark rings. I mean, here you have many different emission points. So basically you could be having many it's not just one, the laser is not just one thin line. So of course there are many different points. And yeah, what we are seeing here with this granular structure, you can see here that it's like glitter. It's very granular here, and I think what we're seeing here could be what my theory predicts, namely wave imprints. So this is not an interference pattern because there's nothing here to interfere. There's no barrier. There's no slits here. But what you're seeing here might be a wave imprint, and 0.1 millimeter is like the smallest distance that you can see with the naked eye. And now you're seeing this through a camera. It's not quite as clear as I'm seeing it. The granular structure is much more clear. So Yeah, it could. Another explanation could be, of course, maybe it's interference from the air in the room. So I don't have a vacuum chamber, so I cannot test that. But it could very well be a wave imprint, which you would not expect that in regular quantum mechanics. Okay, it's pretty late here, 4 in the morning, so I'll go to sleep now. So that's all for now. See you next time.